In this video I am going to talk about the dislocation and how dislocation facilitates plastic deformation in metals and alloys. Before going further into the details of the dislocation, I wanted to show you a movie of a worm, of how a worm moves its body on the ground. In this video you can see a worm that is moving, and during its movement it makes a curve in a part of its body, and by moving this curve it moves its body on the ground, so it doesn't have to sleep the entire of its body on the ground to overcome the friction between its body and the ground. So in the metals and alloys we have crystals arranged of atoms in specific orders depending on the crystal structure of the metal and alloy. In the crystals that are perfect and there is no defect, when we want to make a plastic deformation, we have to apply a shear load. This shear load causes a shear stress. This shear stress is shown here by this arrow, and the shear stress is applied in this direction. Before going into the detail of the discussion, it is worth to mention that plastic deformation is only made by shear stress. Imagine a part of the crystal that we applied this shear stress in this direction, and by applying this shear stress, some planes of the crystal start to move on each other with respect to each other, and because of this movement we have a plastic deformation. So imagine that these two planes move with respect with each other to each other in this direction, and as we continue the application of the stress, these planes moved with respect to each other more and more. But for moving these two crystallographic planes with respect to each other, we have to break a lot of atomic bonds at the same time. For example, in the previous slide we have these atomic bonds, and we have to break all these atomic bonds to move these two planes with respect to each other. And this breakage of the atomic bonds needs a lot of work and a lot of energy. But in practice, the amount of the work and energy that we need to do plastic deformation is much lower than the theoretical value that we calculate for breakage of these atomic bonds. So there should be another phenomenon that facilitates this plastic deformation and the slip of the crystallographic planes. The crystals always have some imperfections and defects. The crystals are not perfect. Various types of imperfections exist in the crystal. One imperfection in the crystal is dislocation. There are various types of dislocations. One of the famous one of dislocations is the edge dislocation. Dislocation means that we discontinue a crystallographic plane. So here we lack a plane in the crystal structure, and this imperfection is named dislocation, and this type of dislocation is named edge dislocation, which we usually show it by this sign. For every edge dislocation we have a dislocation line. Dislocation line is defined along this direction, which is perpendicular to the screen. And also we have a Borger's vector, which is a characteristic of every dislocation. And in the future slide, in the last slides, I will show you how we obtain this Borger's vector. But how this dislocation facilitates plastic deformation? Imagine we apply a shear stress in this direction. By applying this shear stress, recall the movie that I showed you in the beginning, the movie of the worm, how it moves its body. Instead of breaking the entire atomic bonds in these planes, we only need to break the atomic bonds around the dislocation, for example, this bond. And by applying this shear stress, this atomic plane moves to the left side by breaking its let me show you. Yes, by breaking its bond with this atom, this dislocation moves to this direction. So by application this shear load, dislocation moves to this side. And the only bonds that are needed to be broken are the bonds around the dislocation. So we don't need a lot of work and energy to move these crystallographic planes with respect to each other. So we continue the application of the shear load, and we see that dislocation moves to the right side until it reaches the edge of the crystal. And when it reaches the edge of the crystal, we can observe the plastic deformation. So in practice, we have a lot of dislocations in metals and alloys, and the microplastic deformation of every dislocation are summed up together and make visible and macroplastic deformation. But what happens to the dislocation when this dislocation moves? Here I plot you a curve which shows the energy of the dislocation with respect to the location, with respect to the distance. So I named the location of this dislocation A, and the next position of this dislocation is named B. So this dislocation is supposed to move in this direction from location A to location B. So I define two locations here, but I exaggerate the distance here. This is location A and this is location B. The energy state of the dislocation in these two positions is minimum, but when dislocation moves from left to side, we have an increase in the energy of the dislocation because of the breaking of the atomic bonds. And in the final position, when the dislocation reaches the B position, its energy reaches its lowest value again. When the dislocation moves from this side to this side, it is as if this plane moves from right to the left. We have also some forces on the dislocation. In the positions A and B, okay, I cannot draw anything here, so I draw the location B here. In the positions A and B, the amount of force exerted on the dislocation is 0. But when dislocation moves, the amount of the force increases, and then it decreases until it reaches again to 0, and the amount of the force is reversed again, and it again reaches to 0. This position that you see here is named position C, is this position that is a very unstable position for the dislocation, because as you can see here, we have a maximum in the energy of the dislocation, and in this maximum the amount of the load exerted on the dislocation is 0, but it is very unstable, and it finally changes its position from this to the more stable position, which is B. The amount of the shear load that we need to move the dislocation is obtained from this equation, which is G multiplied by sine 2P multiplied by A 1 minus nu multiplied by B and minus sign here. So what are these parameters? We defined these parameters here. B is the Burger's vector, which is the characteristic of the dislocation, and it is defined as the distance between the initial and the final position of the dislocation. This is the Burger's vector. A is the distance of the crystallographic planes that slip with respect to each other. Here, these two planes, these two crystallographic planes slip with respect to each other. So the A parameter, sorry, I made a mistake. This is A, the distance between the crystallographic planes. And as you can see in this equation, when we increase the A value, the amount of the shear stress that we need decreases. So the amount of the shear stress decreases when the amount of the value A increases. This A value is the distance between the crystallographic planes that slip with respect to each other. So we can conclude from this equation that the slip of the crystallographic planes is easier in the planes that are farther from each other. For example, in the crystal of FCC, the planes 1, 1, 1 have the highest distance with respect to each other, and that is why these planes act as slip planes in FCC metals. B is the Burger's vector, and by decreasing the B value, also the amount of the shear stress that is needed for plastic deformation decreases. G is the elastic shear modulus of the material, and nu is the contraction factor of the material. So the most important parameters are A and B. In future videos I will explain you in further detail how this value A is dependent on the crystallographic planes and which planes are easier to slip during plastic deformation. So in the continue I will show you how we can obtain the Burger's vector. For obtaining the Burger's vector, first we select an atom, for example this atom here, and we make a closed loop by beginning from this point. I draw the point like this. Let me show you. I change the color, and I go 3 distances, for example up, 4 distances right, 3 distance down, and 4 distance left, and I reach the initial point. I choose a point here. I do the same, 3 up, 4 right, 3 down, and 4 left. So you can see that we didn't reach the initial point. This vector is defined as the Burger's vector. Thank you for watching.